All right, welcome back. Today we're going to crack a chemical code. And the clues? Well, they're everywhere, in what we eat and drink, even inside our own bodies. Our mission is to figure out the secret agents that keep our chemical world perfectly balanced. And we're going to start with a mystery that might just be sitting in your fridge right now.
So, here's our first clue. Think about it. A can of soda is just packed with acids, right? Carbonic acid, phosphoric acid. So when you drink it, you're throwing this big acidic punch at your body. Why doesn't your internal pH just take a nosedive into some dangerous acidic territory? I mean, it really feels like it should, but it doesn't. And that is our central mystery.
The answer, and yeah, the hero of our story, is something called a buffer solution. It's this incredible, invisible system that's working around the clock to maintain stability. And by the end of this, you and I are going to know exactly how it pulls this whole thing off.
But, before we can really appreciate our hero, we gotta learn to speak its language. And that language is all about the fundamentals of acids and bases. So, welcome to Part 1, our basic toolkit.
To figure that out, we need a really solid definition for what acids and bases even are. And one of the most useful ones comes from two chemists, Bronsted and Lowry. They cooked up a theory that boils down to one simple action.
And here it is. It's so beautifully simple. An acid is just something that gives away a proton. That's a hydrogen ion, H+. And a base, that's what accepts that proton. It's this perfect chemical give and take. Now this is where it gets really cool, because this shows the before and the after. Look at the water, H2O. In this reaction, it donates a proton, so it's acting as the acid. And after it gives up that proton, what's left? OH-, the hydroxide ion. That is its conjugate base. And on the flip side, the bicarbonate ion, HCO3-, accepts the proton, so it's the base. And after it grabs that proton, it turns into H2CO3, carbonic acid. It's conjugate acid. See? They're like dance partners, paired up for this proton transfer.
So the bottom line is, Bronsted-Lowry is all about swapping protons. Now, it's good to know there's an even bigger theory out there, the Lewis theory, that looks at electron pairs instead. It's a wider lens for sure. But for our mission today, this simple idea of proton swapping, it's everything we need.
Okay, so we know who the players are. Now for the next part of the puzzle. How do we keep score? How do we measure their power? Well, that brings us to one of the most famous scales in all of chemistry, the pH scale.
You might look at this and think, oh, the difference is 2, so it's twice as acidic, right? Nope, not even close. The secret here is that the pH scale is logarithmic. Every single step is a power of 10. Let's see what that really looks like. So we've got our first solution with a pH of 1,
And that means its hydrogen ion concentration is 0.1 moles per liter.
Now, our second solution at a pH of 3, well, it has a much, much smaller concentration of 0.001.
So what does that mean when you compare them? That little 2-point difference means the pH 1 solution has 100 times more hydrogen ions than the pH 3 solution. That's the power of a logarithmic scale. It's like a chemical earthquake scale, where every whole number is a massive 10-fold jump in power.
So we can define them. We can measure their strength. Now let's see what actually happens when they meet. We can watch this whole interaction play out using something called a titration curve. And this is where we're going to start seeing our buffer superpower in action.
All right, here's a classic to start. We're starting with a strong base, think sodium hydroxide, and we're slowly dripping in a strong acid, like hydrochloric acid. You can see the pH stays pretty high for a while, and then, bam, it just plummets this huge dramatic drop right in the middle. That super steep part is called the equivalence point. It's where the acid and base have perfectly, completely neutralized each other.
But things get way more interesting when you bring a weak acid to the party. This curve, it tells a totally different story. We start with our weak acid, we add a strong base, and notice there isn't just one steep drop. There are these different zones, A, B, and C, that are absolutely crucial to our investigation. Let's zoom in and decode this thing.
And this lays it all out. Point B, that's our equivalence point again, neutralization is complete. Point C is way out there, where we've added so much base that it's the only thing that matters anymore. But the real magic, that's happening at point A. Look how flat that part of the curve is. Even though we're adding a strong base, the pH is barely budging. It's resisting the change. This amazing area is the buffer region, and it is the key to our entire mystery.
Okay, this is it. We have all the pieces of the puzzle. We know about conjugate pairs, we get how pH works, and we just saw a buffer region with our own eyes. It is time to put it all together and finally crack the case of the buffer solution.
So, let's officially meet our hero, the buffer solution. What is it? It's a mix. It's a team-up of a weak acid and its conjugate base, just hanging out together in the same solution. And its superpower, as we just saw on that curve, is to resist changes in pH. It holds the line.
So how in the world does it do that? The secret is all about this equilibrium, this balance. You've basically got a reservoir of both the weak acid and its conjugate base. So if some rogue acid shows up, the conjugate base is right there to gobble up those extra protons and neutralize it. And if a strong base attacks, the weak acid steps in and releases its own protons to fight it off. It is the ultimate chemical shock absorber.
And what's really cool is you can make these things in a few different ways. You can just straight up mix a weak acid with a salt of its conjugate base. Or, and this is exactly what we saw in that titration curve, you can just add enough strong base to a weak acid to create its conjugate partner right there in the solution. Either way, you get that perfect pH stabilizing team.
And that brings us right back to where we started, your soda. Your blood is one of the most sophisticated buffer systems out there, based mostly on carbonic acid and its conjugate base, bicarbonate. So when you drink that soda, that buffer system immediately gets to work, absorbing that acid and keeping your blood pH locked into the incredibly narrow, safe range you need to live. They really are the invisible heroes, constantly maintaining that perfect balance.
So there you have it. We cracked the code. We saw how this simple little transfer of a proton, when it's organized into a buffer system, can perform the vital, life-saving job of maintaining stability. Which, it leaves me with one last question for you. What other invisible chemical systems are out there, keeping our world stable right this very second? The chemistry is all around us. You just have to know how to crack the code.